SwayamPrabha. Digital India. Educated India.
Welcome back, and last time what we are doing is we are looking at the Kelvin-Voigt body and the response of the Kelvin-Voigt body to an applied stress. And we used very similar methods to what we had originally done for Maxwell's body, and we derived the constitutive equation that this particular system suggests, right. And we ended up with an equation that is linear ODE once again in the stress and the strain, and you have the stress here as expressed as a function of the strain plus the strain rate multiplied by suitable factors. So, now just like we had done for the case of the Maxwell system, we are going to look at jump conditions, right. So, let us look at jump conditions. Okay. So, jump condition. So, let us say the first thing we are looking at is jump condition in strain. Okay. So, I am going to express my strain as some epsilon naught times the Heaviside function. Okay. And just to remind ourselves, what was the Heaviside function? H t is the Heaviside function and H t is basically given as 0 when t is less than 0, equal to 1 for t greater than 0. Okay. So, this is our Heaviside function. So, if you have a jump in strain, let us say, and you want to find out the effect of that on stress, then what we can do is we can straight away insert this functional form right here. But before we do that, there is one more thing that we have to know. We have a derivative in stress, derivative in strain, right. So, what happens if you take the derivative of this function? So, we know that the derivative of the Heaviside function is the Dirac delta function. This is the Dirac delta function. So, your epsilon dot so, if you are taking the derivative of this quantity, the previous functional form, then you will have epsilon delta t. Okay. So, if we use our constitutive relationship to find out the resulting stress, then we get stress equal to E epsilon naught h t plus eta times of epsilon naught del t. So, now if I just want to simplify and I want to write for only t equal to 0 cases, then this implies that the stress is given as E times epsilon naught plus eta times epsilon naught delta t, which implies that we have, if I divide both sides by epsilon naught, then you have, and this quantity is my stress relaxation function. Okay. So, you have sorry. So, I have taken E as common. So, you have eta by E, right. So, I am just going to write that as lambda again. So, just remember where lambda is equal to. So, this should remind you that this functional form is something that we also got in the Maxwell case. Right. So, this is a form of a this is a response time of the system that is the same in both the cases. Okay. So, we have this functional form, but what does this mean? So, if we had to plot our results, so let us say you have here you have epsilon versus time, you have so in this case what you are doing is this, you are applying a known strain to the system, and then you are studying what happens to the stress history. So, what will happen is, because of the delta function, there will be a very sharp jump here, which will be the form of a delta function, which goes towards infinity, and then immediately at any other value of t, this will come down to a constant value. Right. So, we can see that the stress relaxation function is not really very realistic in this case. You have a very sudden jump, and then it comes back, and then it stays constant. It does not decrease to 0, which tells you that this system almost behaves like a, or not almost, it behaves like a solid at times greater than t 0, right. So, this is sort of a viscoelastic solid response. Okay. So, now let us take, we have, so we just looked at a jump in strain, right. So, what we want to do now is to look at a jump in stress. So, to look at a jump in stress, what we are going to assume is that instead of a direct jump, you have the jump as a series of functions that go from 0 to a value of 1 or sigma naught here in a short period of time. This is minus delta, this is plus delta, and the biggest deviation occurs between plus and minus delta, right. And that you have a series of such functions such that you are basically going to take the limit of delta tending to 0. So, to do that, what we are going to use is, we are going to use the previous this constitutive equation, and then we are going to integrate over this small time scale of plus minus delta, right. So, let us do that. So, we are integrating both sides. And here you are integrating if the strain, so if the stress is bounded, then, so by the way, this is once again this is not very mathematically rigorous. So, what I am trying to show you is slightly a hand waving argument here. A more detailed course will go through the mathematical rigor that is required to get to this, but the idea is sort of similar, that you consider a set of approximating functions that rise from 0 to a value, and you take them that they differ from the required functional form in a very short time interval, minus and plus delta. And in this particular case, what you have is you have some bounded number multiplied by delta, right, 2 delta here, similarly here. And as you take the limit of delta tending to 0, both these two terms will end up going to 0. And here you will be left with epsilon 0. So this is going to give you the jump in the strain. So epsilon 0 plus, and because these are 0, you will end up with a 0. Now there is an important issue here. We could not apply this in the previous case, and the reason for that is in this particular system you end up having, so just take a look at this functional form, that the stress has a delta function. The delta function is not a bounded function. In fact, it is not even a proper well defined function. It is, we use it for its particular properties, but it cannot be used in, it is not a regular function in that sense. So this functional form here is not bounded, and because it is not bounded, you cannot use the idea that this will go to 0 because delta is tending to 0, because you might, one term is tending towards 0, but the other term, if it becomes unbounded, then you will not have that situation, right. So that is why we had to use two different arguments for the system here to get our jump conditions. So now let us take a look at, so now that we have the jump conditions with us, let us take a look at the creep response. Creep response for a Kelvin-Meyer-Voigt body. So for creep response, we have to, what is provided to you is that sigma t is equal to sigma naught for t greater than 0. And now we have to solve this particular equation, epsilon dot plus E by is equal to 1 minus eta naught sigma naught. So this is your governing ODE for t equal to greater than 0. Okay. So this value is constant here. So again we have to apply the method of integrating factors. So again apply method of integrating factors. So your Vt in this case, once again you will see that it ends up as the same quantity e to the power t by lambda. So we are left with, so this implies that we have sigma naught, right. Now we will integrate both sides from 0 plus to t. Okay. So you have e to the power t by lambda. I will just use some other variable because you already have e to the power s by lambda into epsilon s. This we have to consider between 0 plus to some time t, and on this other side we are just going to integrate this particular form. So you have plus cos to t e to the power t by no. So again we have to apply some other dummy variable here into sigma naught ds. Right. So you end up with you'll end up with an exponential into t to the power t by lambda epsilon t, and epsilon 0 plus is 0 that we just did. So this is the entire left hand side, and on the right hand side you will have so this is e to the power s by lambda into lambda by eta sigma naught. This goes from 0 plus to t. So you will this will become 0. So lambda by eta is 1 by e. This is so your epsilon t is equal to sigma naught by e. This is 1 minus, I am taking the exponential onto the right hand side. Right. So now my final objective is to find the creep function. So what I do is I take this sigma naught onto this other side. So my epsilon t by sigma naught, which gives me the creep function, is equal to 1 by e 1 minus e to the power minus t by lambda. So this is now your creep function for the Kelvin-Voigt body. Let us plot this so that we get a feel of what this response really looks like. So you are applying a stress, a constant stress. So you will be applying sigma naught here, and then you are going to measure what the creep or the strain value is, right. And what you will get is this particular curve. You will get a curve like this, which asymptotically reaches some value. This is your exponential curve right here, and this represents your creep response function for a Kelvin-Voigt body. Now you can ask yourself whether this is physically realistic or not, and the answer is that it does not look very satisfactory because it starts from a value of 0. If you recall that the intuitive diagram that we had drawn, that there should have been some quick elastic response to an applied stress, and then there should have been increase with time, but that initial elastic response is totally missing in this particular case. So even though when you looked at the stress relaxation function that behaved as if the Kelvin-Voigt, this particular system has a very strong solid body like response, the creep function does not reflect all of that. It does saturate to a value, but here you do not have that. So this is acceptable probably in some cases, but it is not a very satisfactory case. Okay. So we have had the creep response and the stress relaxation function. So we will quickly look at response to an arbitrary strain. That is what we had done for the Maxwell model. So the first thing that we had looked at there was response to arbitrary strain history. So basically you have provided a strain history of epsilon s is provided to you for all values of time leading up to t, and the question is what is sigma t. Now, if we go back to that equation, the governing equation for this particular body, then we have a very simple form, right. So, we have sigma t is equal to E epsilon plus eta epsilon dot t. So, given a arbitrary strain history, all you need to do to find out the current stress, value of stress, is you simply have to compute this, right. So, you can just directly find it. So, if you are given this particular functional form, then all you need to get this result is to just plug it in here and compute it directly. So, this is really easy in that sense. So, now let us look at the other case, which is, so this becomes more or less very simple. So, the response to arbitrary stress history. Right. So, if you want to do that, then basically your stress is provided to you as a function of time leading up to all values till t. And the question is what is epsilon current value of strain. Now, to do that, we realize that what we have to solve is basically the same thing, linear ordinary differential equation, which is non-homogeneous, and that has to be solved, right. So, for that, once again we will need an integrating factor, and an integrating factor in this case and an appropriate integration factor you will see again is the same form t by lambda. Okay. So, in this particular case what you will get is, if you apply this integrating factor, and you will end up with e to the power t by lambda epsilon t equal to e to the power t by lambda sigma into 1 by eta, which is, so now we have to integrate both sides from 0 plus to t, and you have the exponential t by lambda. So, I am just going to use a different variable here for a second. So, say the exponential s by lambda into epsilon s, this has to be found out from 0 to t, and you have on this side you have by eta 0 plus to t e to the power t by lambda, you have sigma as a function of s. So, we are just going to use the dummy variable s for time. And we know that epsilon 0 plus is 0. So, if you apply that, then you will end up with epsilon t by, sorry, this is exponential function. So, the exponential t by lambda multiplied by epsilon t is equal to this particular 1 by eta integral 0 plus to t Now, I am going to not complete this, and I am going to sort of leave this for you as a homework problem. So, you have to integrate this by parts. So, once again you see that you have the functional form sigma s, whereas what you would want is a sigma dot. So, what you can do is integrate by parts. Because I have done it for the previous case, so I will leave it here, integrate by parts to obtain. And what you will find is, to your surprise, that the strain is still given by the same functional form that we had gotten for the Maxwell model. Okay. So, this is and this is rather interesting because the two creep functions are very, very different, yet when you try to find out the strain history, the strain from the stress history, you end up with a functional form that is exactly the same as the Maxwell model. So, this indicates that this particular functional form that we are seeing, that I have boxed in red, is a more generic equation that governs such models. Okay. So, for today we will leave it here, and the next class we will look at once again quickly a comparison of the Maxwell and the Kelvin-Voigt model, and then we will go on to make more complicated models for ourselves. Okay. So, we will stop here today.